An important tool in physics that we use a good bit through all of the problems that we'll be solving throughout the year are called free body diagrams. Free body diagrams are also known as force body diagrams and also just generally force diagrams. Free body diagrams are integral to understanding the characteristics of a particular system and whether or not objects are interacting, accelerating, moving, and so forth. And so there are some key pieces of a free body diagram that you'll need to be familiar with. The most basic idea is that it isolates the object in question, which is what makes it free, right? And then it depicts all the forces acting on that object. What we mean by isolating the object in question is that when we draw the forces, we are careful to draw the forces that are only acting on the object in question and not forces that would be acting on other objects in the system. And I know it'll make sense in just a moment when I show you an example, but I do want to mention that when we depict the forces, right, these are done by drawing arrows, right, where it's important to recognize that arrows serve two main purposes, right? First of which is the obvious one, which is direction, right? And so if the force is this way, the arrow is that way, and if the force is this way, the arrow is that way, etc. But it also depicts magnitude. Magnitude is a scalar value of a measurement, which essentially is amount, which in terms of forces can be thought of as strength. So if I'm pushing to the right and I'm pushing relatively hard, I can imagine that the force would be a much longer arrow than if I was pushing very softly to the right. Right? If I'm pushing even less, then I would push less. The nice thing about the course we are in, we are not going to worry about exact proportionality. So if I say that one force is very large and one force is very small, that's sufficient. If I do know that one force is approximately half of the other or one is double than the other, I'm trying to draw those lines essentially in scale, but they don't have to be perfect because we're not actually going to measure them. They are simply for reference for you as you build a system. All right, and then of course it'll be important to label which ones are which so that you know what forces are acting. And so the most common example is to think about an object falling, right? And so there are a few different scenarios. Let's say that I hold an object up in the air. Let's say it's a baseball held in my hand, right? If I have the baseball held in my hand, let's say it looks like this, right? And I am supporting it, it is not moving, and it's just sitting there. This would be a picture of the scenario. It is not the free body diagram. If you are asked for a free body diagram of the baseball, then I'm going to separate and free up the baseball. So I'm looking simply at the baseball only, right? I recognize that in the real world scenario, the hand is there, things are touching and interacting, but when I draw the free body diagram, I isolate only the object in question. So looking at this baseball, when I'm labeling the forces, I'm careful to label all of them and think logically about the scenario. I know that the baseball is at rest. I know that it is not going up or down, which means that it is most likely at a state of equilibrium, and therefore the forces are balanced or there are no forces acting. Now, of course, no forces seems highly unlikely since almost always there is the force of weight, which is the force due to gravity, force G in this case. But since the ball is not falling down, I'm going to be careful to draw a secondary force acting up, where I'm indicating that these two are essentially the same magnitude in opposite directions. I'm labeling this, in this particular case, as F, and then since this is not a specific force due to some standardized physics occurrence, but instead due to the hand, I'm simply writing the force due to the hand. There are tools where I could indicate that this is the same length as that by doing something like that, like you would see in congruency for triangle sides in math class, but it's not entirely necessary for reasons I mentioned before. The scale is simply for you to judge. But nevertheless, if I look at a different scenario where instead the hand, oh my, the hand is throwing the baseball up, where this is going to launch into the air, right? In order for that to launch into the air, and I'm asked for the free body diagram of the baseball, I isolate the baseball, I draw solely the baseball, and then I look at the forces acting on it. In this case, the force of gravity is still there, F of g. But now I recognize that from the scenario that the ball is accelerating upward because I'm throwing it, and so ultimately it is going to go upward. This is easily depicted by simply drawing the force of the hand higher. This diagram shows me that the force of the hand is in the opposite direction as the weight, but it also indicates that the force of the hand is greater. And as we go through Newton's laws, we'll realize that the larger force outweighs the smaller force, which is the result, or the result is this ball accelerating into the air.